Good afternoon. So in this video tutorial, I'm going to discuss the startup time of a CSTR. So we'll discuss the derivation of the equation. Let me share the PowerPoint. So startup of a CSTR. So CSTR are always in continuous operation. So to get this to steady state, you need to start up. This process means start from some initial condition to a final condition. So initially, if you're going to feed the reactant to a reactor, a CSTR in particular, so that means in the initial state or the startup, it's not going to produce the product that you desire. So you need to run this for a couple of minutes or a couple of hours before it becomes a steady state. So the objective of this tutorial is to find out how much time do you need before the steady state is achieved. Okay, so why do we need to start up a CSTR? So probably we have a new process, no? A new equipment is installed, or we have a quality or maintenance shutdown. There's an electrical failure, so this also results to a shutdown. So we have scaled up or scaled down the process. So these are the reason why we need to start up a CSTR. Okay, so time necessary to achieve steady state. This is what we're going to calculate. The equation for this, the time necessary to achieve steady state, is what we're going to derive later. So if you will imagine, concentration and conversion are function of time. Generally, as time passes by, the conversion increases and the concentration of the product increases while the concentration of the reactant decreases. So we'll be deriving the first order analytical solution, the first order equation. And then for the second order and up, probably you can use the polymath to solve the problem. Okay, so we have here the mole balance equation for a CSTR. You still remember this? FAO minus F sub A. So if you still remember, F sub A is the molar flow rate of component A. Probably I can annotate this. So FAO Mama, ayos umulat ng ballpen ko. Pakisaksak mo nga ulit. Ayan. Wala? Mama, ayaw pa rin. Saksak mo nga ulit. Ayan. Yung sa baba. Yung maliit sa baba. Yan. So FAO and also FA. So if you still remember, these are the molar flow rate. So for example, this could be mole per second, kilogram mole per second, etc. So if you have a CSTR, basically this is your FAO, and then this is F sub A. So that's why whatever is generated by the reaction, R sub A times B, uh, this is added to the FAO minus F sub A. So this is added because R sub A is generally equal to negative KCA. Ganun yung convention kay Pagler, ano? At saka kay Liebenskill. R sub A is equals to negative K, C to the A, times C to the A to the N. Tapos, since wala pa tayo sa steady state, this term, yung change the number of moles per with respect to time is not equal to 0. So that's why ito yung ating working equation sa start of a CSTR. Okay. So what we're going to do is we will suppose that 99% of the steady state concentration is when we achieve the steady state. Ano? Ito yun. Ito yung ating condition. Ano? 99% ng steady state concentration. Pag na-achieve yun, yun yung time na tatawagin natin na ano, na hinahanap natin. I hope you get this one. Equation. Okay. So we'll just change FAO. We'll just replace FAO with CaOBO and then FA with CaB. This is the flow rate going into volumetric flow rate going into the CSTR. This is the flow rate going out of the CSTR. So CaO is the concentration. So this is in moles per liter, for example. And then, if for example, this is in liter per second, yung flow rate. So as you can see, this is mole per second. So it's equal to your mole per second, molar flow rate. So that's the justification for this equation. Dimensional analysis lang naman. Ano? So we have CaO times BO minus Ca times B plus RAB is equals to DNA dt. And then basically we're just going to divide this term with the volumetric flow rate. So what will happen is if we're going to assume that these two are equal, mawawala na yun. Ano? So you have CaO minus Ca plus RA B over B. B dot. This is small b, ano? DNA dt 1 over B dot. And then B over B dot, this is simply equal to the residence time. Ano? This is the residence time. So that's why in this equation here we have CaO minus Ca plus RA times the residence time. Parang nasusunog. Is kain ka ba? Okay. So DNA. And then what we're going to do right here is we multiply this equation with B over B. This is just volume over volume, so that we can generate another tau on this side of the equation. Okay. So next, I hope you're following the derivation. We're going to clear this up. Okay. So we have a tau here because the B over B is tau, and then NA over B is Ca. So we have a homogeneous differential equation. Okay. So you can for non-first order or non-zero order reactions, you can just transpose this tau on the other side of the equation, and then the equation that will result, you can use that in the polymath. to get the concentration versus time. Of course, you need the initial concentration and the tau value. So you need the volume of the reactor and the volumetric flow rate. Plus the equation for your rate of the reaction. So whether it's KCA or KCA times CB, you need that, no? Okay, so what we're going to do is we're going to derive that the startup time for a CSTR when you have a first order reaction. So for a first order reaction, R sub A is equals to negative KCA. So we're going to substitute this equation over there. So when you substitute it, we have this equation CAO minus CA minus KCA tau is equals to tau dCA dt. Okay, as you can see, CA is factored out, and you have 1 plus K times tau is equals to T tau dCA dt. So you just simply divide both sides of the equation by tau, and you have CAO tau divided by tau minus CA, 1 plus K tau divided by tau is equals to dCA dt. So if CA is equals to CAO, when T is equals to 0, you can solve this differential equation. This is the solution of that differential equation. Ano? CA is equals to CAO, 1 plus K tau times 1 minus E to the negative 1 plus K tau raised to T divided by tau. Okay, so this is the solution of this differential equation. First order, no? Okay. So as you can see, if time is infinite, that would be the steady state concentration. No? So if time is infinite, this time here is infinite, this part of the equation will become 0. So CA steady state is equal to CaO 1 plus K tau. So I hope you get that. When this approaches infinity, no, CA would become the steady state concentration, and that would be equal to, when this becomes 0, this is the steady state concentration. CA is equal to CaO 1 plus K tau. Now, we only wanted to, in calculating the time for the CSTR to become a steady state, we only wanted the concentration to be equal to 0.99 of C sub A steady state. No? So we're going to replace CA with 0.99, CaO 1 plus K times tau. In the next slide. Ito yon. This is the steady state CA. It's equal to CaO times 1 plus K tau. So just multiply it with 0.99 and then replace CA with 0.99 CAS. And then CAS is CaO 1 plus K tau. So as you can see, this will cancel out. No? CaO 1 plus K tau will cancel out. So we can with this we can solve tau. T. We can solve T. So you can use your calculator to sheet solve it. But let's derive an explicit equation, much better. So starting from the last equation, 0.99 1 minus exp. Sundan nyo? So 0.99 1 minus exp minus 1 plus kt raised to t divided by tau. That's the equation. 1 minus e raised to negative 1 k plus t. So just transpose 1 to the other side of the equation, or transpose point. What did you do? I transpose 1, so you have negative 0.01. Tapos you take the ln of both sides of the equation. So negative ln, so that you only have this one, ano? Kasi this is, yeah. So this is the equation. No? So ln 0.01 is simply 4.6. You can use your calculator. Then transpose tau. And then transpose 1 per kt. So this is the equation for, ano? This is the equation for first order. No? T is equals to 4.6 times tau 1 plus, this is the reaction constant K times tau. Ganun lang kasimple ang CSTR time. No? Okay, so let's try to solve a sample problem. Okay, so consider this reaction A to B. This is an elementary reaction. Okay, stated. So what's the consequence? So the consequence is R sub A is equals to KCA. You know, so this is a first order reaction. So we can use our equation to solve this problem. K is equals to 2.2. So probably per second. So probably the unit here is per second. And then the rate of the reaction, this is the volumetric flow rate, 0.05 liter per second. And then the initial volume of the reactor is 2.5 liters or 2.5 decimeter cube. The initial concentration of A is 0.05 moles per liter. So simply use the equation for CSTR startup time. So T is equals to 4.6 K tau divided by 1 plus K tau. Okay. So if you still remember, tau is simply the volume of the reactor divided by V. So solving for time. So we have 4.6, okay? So times K is 2.2 per second. And then tau is volume, 2.5 liters, divided by volumetric flow rate, that's 0.05 liter per second. So as you can see, this will cancel out. This is seconds. This is second per second, so this also will cancel out. Okay. Sa denominator, we have 1 plus, again, K is 2.2 per second. And then, again, multiply this with 2.5 liters and 0.05 liter per second. This will cancel out. Okay, so this is supposed, using the calculator, this will give you something like, oh, 4.6 tau, wala palang K doon. Sorry. It's supposed to be 4.6 tau. Okay, here. So that's why the unit would be seconds. Ano? So, so you're supposed to get okay, 2.0, 2.07 seconds. Ano? So T equals to 2.07. Okay, so in the final exam, just try to remember this equation. T is equals to 4.6 tau all over 1 plus K times tau. Okay, so there's another topic, the semi-batch reactor, and then you can answer the final exam. So I'm planning to give you a midterm removal exam. So please answer the final exam and the midterm removal exam so that you can get a passing grade on this course. See you on the next video.